Have you ever noticed that when you are going through the cloverleaf on a freeway, or if you're on a roller coaster, or how about this improbable situation here where we've got the motors? No, I didn't do anything to that picture. That is really as steep as that bank is. Why do we have these banked turns? If I'm driving in my car and my turn is flat, as I go through the turn, I'm going to want to continue moving in this straight line, okay? But the friction of the tires on the road, so I want to move this way, but I end up going this way. And remember, friction opposes motion. So if I turned in, then friction must be the force that caused me to go in, because I want to go this way, but something had to pull me back this way, and that was the friction of the road. So on an unbanked turn, I would basically have to rely just on friction in order to get me to go straight. So friction is my centripetal force. The force of friction is my centripetal force when the turn is unbanked. So remember, this is mu times the normal force, and this is mv squared over r. And then if I'm on just a flat turn, so it's flat, and here's my car, okay, here's my gravitational force, and here's my normal force. So my normal force is actually equal to my gravitational force when it's flat. So mu times, remember, my gravitational force is mass times 9.8, or mass times gravity. Mu mg is equal to mv squared over r. So my masses will cancel. So it doesn't matter what the mass of my car is. It matters the friction on the road. Okay, the coefficient of friction between my tires and the road. So when it's wet, okay, that's why we have to drive really carefully when it's wet. When it's wet, the coefficient of friction decreases. And so, mu is equal to v squared over gr, if we rearrange it. Or we could say, if we wanted to rearrange it so we knew how fast we were going, we would say v squared, v squared equals mu gr. So v is the square root of mu gr. So when it's an unbanked turn, so here we're talking about unbanked turns, how fast I can go through the turn depends on that coefficient of friction. And when it's wet, that coefficient gets to be smaller, and so I have to go slower through the turn, or I'm going to slip and I'm going to crash off here somewhere, and that's not good. So what we do is we bank a turn. We bank a turn so I don't have to rely on friction. Okay, on an unbanked turn, the only way I can make the turn is with friction. Once I bank that turn, now I don't have to rely on friction. So let's see how. Okay, so our banked turn is like an inclined plane. Okay, so remember, your normal force is going to be perpendicular to your plane. So that's why our normal force comes up this way. Okay. Now, remember when we were jumping that the normal force responds to other changes. Okay? In this case, the normal force is going to respond to changes. So we have the normal force and we have our weight. Those are basically right now the only two forces. We're going to ignore friction for right now, but we could add in friction later. So don't forget that. these two forces are the only forces we're worried about right now. So our car is in equilibrium vertically, okay? Meaning it's not popping off of the ramp, which means this, the component of our normal force that is in the y direction, so now we're doing x and y. So x and y, the component of our normal force that is in the y direction has to cancel out our gravity. So these two are actually equal to each other. So the force of gravity is the same thing as our normal force times the cosine of our angle. And it's cosine because this is our angle. Remember when we were on an inclined plane, okay, this angle here was equal to this angle here. Well, look, we're just continuing that here. So this angle and this angle are the same, and that is adjacent to that angle. So katoa. So that's adjacent. This is opposite because this angle and this angle, parallel lines cut by a transversal, are equal to each other. And this is opposite that triangle. So basically what we've done is we've taken the normal force and broken it up into its vertical and horizontal components, which are a little bit different than what we had in the past. Our centripetal force, okay, where's the center of our circle? The center of our circle is out here, okay? So this force right here is providing the centripetal force. See how that points towards the center of our circle? That's our centripetal force. So our centripetal force is n sine theta, or Fn sine theta. All right, so what are we going to do with those two guys? Okay, we have two equations here. We have normal force in both of those. Really, we don't want to have to deal with the normal force because we can't really calculate that. That responds to changes. So let's take them both and rearrange them so that they say the normal force equals. So in the first one, the normal force is equal to mg divided by the cosine of the angle. In our second one, the normal force is equal to our centripetal force divided by the sine of the angle. Okay, so now we have two equations. They equal the same thing, so we can set them equal to each other. mg over cos theta is equal to fc over sine theta. Okay, and remember fc is mv squared over r over sine theta. It's really getting kind of ugly, isn't it? Equals mg over cos theta. All right, so mass shows up in both sides. We can cancel that. That makes our life a little bit easier. This r actually will go on to the bottom because this is like saying v squared over r times 1 over sine theta. Remember when you are dividing fractions, you multiply by the reciprocal? So now we have g over cos theta is equal to v squared over r sine theta. So if we rearrange it so that all our thetas are on one side and everything else is on the other side, we have sine theta over cos theta is equal to v squared over gr. And sine theta over cos theta, for those of you that have been in pre-cal before, is the tangent of the angle. So overall our equation does become tan theta equals v squared over GR. Okay, and that would tell us what angle do we need to bank the turn so that we can go through the turn. Notice that friction was not in here at all. So now I don't have to rely on friction in order for me to get through the turn. I can make this turn on the iciest of days as long as I'm not going too fast. As long as I'm not going too fast, I can make this turn no matter what. And when you're driving, you should notice that it is easier to turn if the road is banked or if it's tilted, as opposed to when the road is flat. That's when you're more likely to skid or something like that. Bottom line. Here is our equation that we will use without friction. Notice this is without friction on a banked turn. Once there's friction, then we have to take into account, but I think you've had enough to think about for now, and we'll derive the with friction in class. So this is the equation you want to use for banked turns. That's the only time you want to use it, though. Don't try to use it every other time. And this is the reason why that equation works. Remember, we're looking at the component of our normal force that is causing us to go towards the center of the circle. All right, guys, I'll see you later. Bye.